Hello, welcome to Petrochronics, a research group and extension project focused on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTt-talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello, everyone. Welcome to our PTt-talk 27th. We are the Petrochronics, a research group where we promote talks and some kinds of discussions with Brazilian researchers and international collaborators about petrochronological techniques applied for geodynamic evolution of our planet. I'm so glad to be here today with our speaker, Christophe.
Hello.
Hello. Christophe will talk about the tectono-thermal evolution of proximal continental passive margin during pre- to early rifting, with a case of the Southern Alps in Italy. I'm Mariana, I'm a PhD student to FMG, and today with me is Maíra, a professor in UFMG, also me. Regiane, that she is professor in Unesp, Rio Claro, and Alice Westin, a postdoc in USP, in São Paulo. Thank you, Christophe, for attending our invitation. We are looking forward to your talk, and I will pass the floor to Regiane, who told more about our initiative.
Hi everyone, welcome to the PTt-talk. Here in the YouTube, we have the PTt-talk series where we share presentations about methodologies and advances about petrochronology. If you miss if you miss the previous talk, don't worry. Just to see the previous presentations here in our YouTube channel, and you accept suggestions about subjects or people for the next speech talks. Thank you, everyone. Now I will pass the word to Alice.
Good morning, or good afternoon, or good night. I don't know when do you going to see that. But I'm going to present Christophe, a little bit of his biography, academic biography. He is currently a postdoc at the University of State of Rio de Janeiro, UERJ. His research focuses on critical minerals in Brazil, developing metallogenetic and exploratory models for sedimentary phosphate deposits in the southern portion of the western edge of the Brasilia Belt. He holds a bachelor's and master's degree in earth sciences from Nice, Sophia Antipolis University, and René One University in 2013 and 2015 in France. He obtained a PhD in petrochronology, structural geology, mapping, and thermodynamic modeling, focused on rift-related geodynamics at the University of Turin in 2019 in Italy. So Maíra now is going to talk about what he is going to present for us.
So hello everyone, we are very happy to have Christophe today. He will talk a bit about his previous work, focusing the preserved remains of middle crust in the former Adriatic Pacific margin, which is exposed in the Southern Alps in Italy. And this area is south of the Insubric Line. And it's interesting because there is no Alpine overprint in this area, which allowed him to reconstruct previous metamorphic evolution of this region. So Christophe will show the results in which he combined petrological constraints with thermodynamic modeling, lutetium, hafnium dating in garnet, and also uranium lead in monazite. And this data allowed him to reconstruct the alpine rifting and the related metamorphism. So thank you so much, Christophe. The stage is yours.
Super. Nice introduction. So you see well the screen? It's perfect?
Yes, it's perfect.
Okay, good. So here it's a view of the field area. So you see we are in good condition. We have beautiful landscape, a very nice place to go in holidays also. Nice mountain, nice lakes. And so we did this project in collaboration with Simona Ferrando, Rodolfo Carosi, Nicolo Spreuzheim, Chiara Groppo, Catherine Fassler, and Daniela Rubato. And this project was inspired by Marco Beltrand. And so we will, as we were introduced, we will speak about structural geology, petrochronology, a little bit of sedimentation also. So I will divide this presentation as an introduction. After, in the first part of the presentation, I will speak about the tectonic link that I can find between the middle and the upper crustal level. In the second part, we will focus inside the middle crust and we will make the tectono-thermal evolution of it doing PTt path. And on the last part, we will make a very short, we will link all the observation that we have observed between middle and upper crust with the basement and the associated overlying sedimentary cover to see if the wall result that we obtain have meanings. And after we will conclude and finish the talk. And so to start this presentation, I'm starting at very large scale, and I will make you understand why we are studying these kind of things in the Alps about drifting. So I took two examples. So I took the Jeanne d'Arc Basin, which is localized here. It's a Triassic sedimentary basin due to rifting, which is located in Newfoundland on the North American side of the continental crust. You can see the continental crust here. And on the other side, on the European crust, there is a fossilized rifted basin like the Monte Generoso Basin that we will study. And you will see that both of these basins are similar, but they are both on one side of the rifting process. And so why we are interested about rifting? We are interested about rifting because we want to understand how a thick continental crust that is like here with normal thickness of 30 kilometers can be extend and can be finished to zero, where you have the asthenospheric and the mantle that is able to reach the surface and making the oceanic ridge and make the seafloor spreading. So we are interested of the precursor of the rifting and how you can thin the crust till you will get the oceanization. And the rifting margin, usually they are divided in two domains. There is the distal margin, where you have the hyperextended margin, where you have very few kilometers of continental crust remaining. And after you have the proximal margin, where you have the initiation of the rifting, where your crust is still thick. And we will be between these two domains in the necking zone here, where you will have extrusion of middle crustal level, because you can see in such diagram that the middle crust is going to be removed, and at the end you have no more middle crust, and there are many outcrops in the Alps where you can find the upper crust and lower crust together, and the middle crust is not anymore existing. So going back, continuing, this is the structure, for example, of an actual sedimentary basin, the Jeanne d'Arc Basin. The Jeanne d'Arc Basin is a world-class petroleum basin, so they are extracting a lot of hydrocarbons here. And this is the basin that are fossilized in the Alps, the Monte Generoso Basin, which has been reconstructed after the Alpine tectonics and restored. And you can see from the structure, we have asymmetric faults and conjugate faults, and you have exactly the same kind of structure. And you can see also that the basin is filling by Triassic to early Jurassic sediments. And also in the Alps, the basin are filled by Triassic and early Jurassic sediments. So we have the same kind of settings, but one was actually underwater, so it's really complex to study it. You have indirect, you have to make indirect analysis, and here you can see everything's outcropping in the Alps. You can delve inside the structure of the rift margin, so it's the best position to identify this kind of basin now for prospection. So this is what I present, and so for the one that don't know the Alps, so I make a quick introduction. So this is the Alpine arc taken by satellite view in winter. So you see it's a beautiful orogenic arc. And it's due to the collision of the European plate on the north with the Adriatic plate. It's a microplate between the European continent and the African continent in the bottom, which is now Italy. I already put the star of the locality where we will be later in the presentation. And to explain a little bit about the Alp unit. So the Alp is divided in two domains. There is the upper plate. So the upper plate is the Adriatic plate, which is this Southern Alps domain in brown color, which are here on the map. On the opposite side here in pinkish violet pale color, you have the European crust, which are here with the external unit, with crystalline massif, and you have all the sedimentary cover, which are basically Mesozoic, Triassic, Cretaceous sedimentary cover that are folded and thrusted toward the external part of the chain, which is here in the northeast. And then in the middle of the chain here, in the greenish color and in pale blue color, you have the suture zone of the belt with the remain of the ophiolite in all blue schist, tectogate-facies condition. There is piece of mantle involved. They are part of the accretionary prism, which is preserved here in blue of the subduction that was between the Apulian plate, which is this domain, and the European plate, which is this domain. So then we want to study rifting, but we have some problem because if you want to study the metamorphism and the structure of the rifting in the Alps, you will face this structural and metamorphic inheritance because in the Alps we have all the Variscan collision phase. So it's an orogeny that was in the Alps at the Late-Carboniferous, Early-Permian, that is due to the collision of two paleocontinents, which is Laurussia and Gondwana. And this orogenic collision makes a metamorphism that is already present with the structures. And then you open this domain and make a passive margin rifting to oceanization. So this is this domain from Permian to Jurassic time. So you might rework this domain by putting a new metamorphic event and new fault. And after that, you have the subduction also during the oceanization. And later on, in the tertiary phase, you have the alpine convergence. And so you will fold and rework everything together. So according to this, you say, I want to study this event. And I'm sandwiched between the Variscan one and the tertiary one. So you could say to me, Christophe, I think it will be difficult and maybe it's not the best choice you did. But we will see in the next of the presentation that there is ways to be able to constrain this and to deal with the polymetamorphic terrain in the basement. So one of the deal to do that is looking at the map of the alpine metamorphism. So we have a lot of data set in the Alps due to many publications. And this is really nice because we have a very detailed map of the alpine metamorphism. So you see it's basically high pressure, low temperature metamorphism linked to subduction zone. And you can see that most of the highest pressure terrain in the Alps are located here in the north of this Insubric Line. This is the Insubric Line, which is one of the major discontinuity in the Alps. And after the metamorphic grade is decreasing progressively toward blue schist, green schist, and low green schist facies condition. And the place where we are studying is here. And you can see we are in the anti zone of the alpine metamorphism. So there is no alpine metamorphism there. Nothing. And this is extremely good because every metamorphic mineral that you will observe there must be pre-alpine. And so we will have only two possibilities then, or they will be Variscan, so Carboniferous, or they will be linked to the Triassic Permian rifting. So we have only to deal with two phases instead of three, and that's way more simple. And so here, this is a cross section that has been made by other co-authors, Schmidt and al., that show the architecture of the Alps to make you understand. So you have the Adriatic plate here, which is like a buttress that will press inside the European crust, which is here. And you can see that all the subduction slide is compressed and exhumed here in this channel. And here you will have the Insubric Line that branch here toward very deep structural part of the belt. So you see you have like almost 40 kilometer vertical fault. So this is this line, the Insubric Line. As I told you before, it's one of the major continuity of the Alps. And it's completely crazy because if you think about it, here in the north, you have coesite or high-grade eclogite condition, and you pass this line, you have nothing, absolutely nothing. So it's huge, huge, huge tectonic boundary, this position. And in fact, this place is really, really interesting for us because as you can see here, it's the passive margin of the Adriatic plate, with in pinkish the basement and in bluish the limestone cover. So the rifted sedimentary basin that are overprint by back thrust. You can see the back thrust due to the compression. But you can see something super interesting. You can see that the middle crust, the lower crust, is progressively folded till a vertical position. So what does it mean? It means that when you will arrive on the northern part of this domain here, you will have a verticalized cross section of the basement. So here you have a natural cross section of the basement of the whole crust of the Adriatic plate going to the north, and this is absolutely perfect for geologists to understand what's going on in the middle and lower crust of the Adriatic plate. And so this is what we will do. So here is the map of this domain. And you can see, as I told you, in the bottom part, you have all the sedimentary basin, which is Jurassic sediment with some Permian volcanic rock, with some Cretaceous fifth molasse close to Milan plain. Oops, sorry. And in the north part, you have the tilted basement that outcrop. And this is all the Paleozoic basement of the Southern Alps. And this is exactly where we will study our rifting inheritance. And we will divide this place in 3 units, the Domato-Cortafo zone, the Dervio-Olgiasca zone, and the Monte Generoso zone, which are the 3 domains that we will study now. And so this is the geological map I did from these 3 units. And so the Domato-Cortafo zone, the Dervio-Olgiasca zone, and the Monte Generoso zone in the bottom, and here in bluish, there is the sedimentary cover of the basement. So I will explain more this geological map after, but before I would like to start my first part after this very long introduction is which are the tectonic links between the middle and upper crustal level according to rifting. So let's see what's going on there. So I retake again my picture that I showed you in the beginning of the presentation in the introduction about the Monte Generoso Basin. And this is a very beautiful work that has been by Bernoulli and Bertotti in the 90s. And they show, like in this cartoon here, that in the Alps, you have preserved normal faults that are east-west. They are going to the east, these faults. And later on, by the Alpine shortening, which is north-south, you will have compression of this old normal fault. And as you can see, you will have a folding of the northern line of the normal fault of the disdetachment. And this is really good for now for geologists because you will be able to walk on the upper part here of the fold and you can touch the fault and you can see like a natural cross-section of the fault in the basement. Because if you look here, I have put the arrow to you to simplify and indicate where we are. So this is this part here that is folded. And so more you will go to the east in the profile, more you will go deep in the fault system. So in the beginning, where there is these 2 green arrows, you will be in the contact between basement and sediment, young sediment, basement, and after you will be older sediment, basement. And after, when you will are in the deepest part of the fault, you will have basement to basement. And this is exactly what happened here. You will have sediment basement, and here basement. And this is extremely fantastic, this section, because when you are in the shallow crustal level, the basement is really affected by numerous brittle events, a lot of cataclysite, a lot of brittle deformation. And more you will deep inside the domain, more you will have mylonitic deformation that will came. And so till the end where you have fully melanitic. And so this is really, really nice for geology. And this is how this fault appear on the field. So this is the Lugano-Val Grande Fault. And as I told you, the northern line is verticalized. And you can see here on the landscape, there is like a depression. And this is the fault that separates the Dervio zone from the Monte Generoso zone. And after it's continuing, it's folded and passed behind toward the Monte Legnone and Legnoncino there. And so this is the Lugano-Val Grande Fault on the geological map, as I told you. And so this is really nice, this fault, because this detachment, as I showed you before, it's making exhuming this part of the middle crust of the Adriatic plate. And due to this detachment, this is going to the east part, you can exhume the middle crust and investigate it to understand the rifting process that has affected the Adriatic plate. And so this is what we will study now. And this section is really beautiful of the middle crust because you will have in the bottom, you will have an increase of metamorphic grade in the bottom. You will have chlorite albite mica schist with some, no, what, sorry, white mica chlorite albite mica schist. And more you will go to the north, in the more you will increase the metamorphic grade. After you will move to muscovite, biotite, staurolite, garnet mica schist. And after you will enter in the granulite facies condition and you will have sillimanite, garnet mica schist. So you will have a very homogeneous, continuous increase of metamorphic grade toward the north of the unit. And as you can see on the map, I have drawn the main foliation traces. You can see that the foliation traces is mostly east-west and is mostly not deviated by the topography, and it's because it's subvertical. And as I told you before, the continental crust here is completely folded, and we have vertical features. So this is a beautiful cross section here inside the crust of the Adriatic margin. And so here, this is, for example, the cross section with the ice grade like staurolitine, sillimanitine, and the evolution of the Lugano-Val Grande Fault that goes toward this position. And in fact, if you look inside this fault domain, this detachment, what you can observe when you are more shallow domain, you will observe cataclysite, many brittle deformation, crushed rocks. For petrologists, it's a bit dirty, so it's really difficult rock, but it's all brittle rocks. And more you will move toward the east inside the fault domain, more you are deeper in the structural domain, and more you will start to see this kind of things. You will find mylonite. There are a lot of mylonite that are reworked by cataclysite, by the exhumation of the footwall. And in fact, on the geological map, when you are toward the footwall, which is the Dervio unit, you will find mylonite. And when you are toward the hanging wall, you will find cataclysite. And this is really systematic of large-scale detachment on the field, where you will find juxtaposition of cataclysite and melonite. Cataclysite to the hanging wall, melonite to the footwall. And in fact, if I look these two guys inside fin section, here I see my brittle deformation, and here I will see my ductile deformation with, for example, here a white mica fish. And then if I move more to the north in more deeper structural level, I will find more plastic deformation, more ductile deformation in the fault system with mylonite and even high strain mylonite with some ultra melanitic band. Very beautiful, this one, very beautiful outcrop. With systematically top to the east, kinematic top to the east, always, because we are exhuming the Dervio zone. And in fact, if you look inside the fin section again, you will see that now we are entering inside the stability field of the biotite, and you have not anymore only white mica deformation, you have also mica fish of biotite. So you are increasing the condition of the mylonitic system. of the metamorphic grade. And so now that we know this, we will start to make to try to constrain the tectono-thermal evolution of this middle crust that has been exhumed. So we will try to constrain the PTt-talk evolution of the middle crustal part of the Adriatic margin. So this is some picture of the locality. We have beautiful landscape, and we were very lucky about this. And so this is what I described previously. So you have an increase of metamorphic grade from chlorite mica schist to staurolite mica schist to sillimanite mica schist. And so it looks like a Barrovian sequence, so something really classic. But we will see that we can question this. Is this a true Barrovian sequence? Like, does it make sense? Does it prograde metamorphism from the continental crust? And so this is what we will investigate right now. And so I will start with the middle of the unit. I will start with the staurolite part, and you will understand why. So this is how the rocks appear on the field. You have beautiful porphyroblasts of staurolite, sometimes with the twinnings here, very beautiful. And if you look them into more detail, you can see that these porphyroblasts of staurolite, they are well deformed by the main foliation of the mica schist. But if you look well into detail, you can see that inside the porphyroblast, there is a preserved old dust deformation here. You can see some folding from the orientation of the quartz inside the porphyroblast. So basically, you have an old dust foliation inside these rocks that were axial plane refolded by the new one, which is pervasive. This is what I have shown here in the cross section. And now, if you move more to the north and you increase the metamorphic grade and you enter in the sillimanite stability field, what you observe on the field? You observe something really specific on the field, very strange. You observe this kind of ball that are on the foliation plane. But if you look carefully about them, they look like garnet, but it's not garnet. It's all biotite and sillimanite. And in fact, if you look inside the thin section, what you can find is sillimanite fibrolytic plus biotite ball inside your thin section that are wrapped by a foliation made of biotite, white mica, quartz, and plagioclase. And in fact, if you look the structure of these rocks, you can find it's weird because sillimanite and biotite are extremely weak mineral. And if you apply a deformation to this class, you will completely crush it, you will erase it, and this cannot survive to deformation. And this is why this is pseudomorph after garnet. So this guy was a garnet before, and he was a porphyroblast inside this main foliation, and after it was statically destabilized into an assemblage of fibrolytic sillimanite and biotite by an increase of temperature, and a decrease of pressure because you are dissolving garnet, so you must decrease the pressure. And so this is really beautiful on the field. And in fact, if you hammer this ball, you will have only sillimanite and biotite. And this is the pseudomorph of the field. And if you look carefully in some pseudomorphs, you can see that they're overprinted. You can see that sometimes they're garnet, and you can say, but it's the garnet which is deformed by the main foliation. But if you look carefully on this, you can see that it's not the case. You can see that inside the pseudomorph of the sillimanite and biotite, there is a new grow of a new garnet. And so if you don't pay attention, you will confuse and say, it's the garnet from the main foliation. But it's not the garnet from the main foliation. It's the porphyroblast. It's a new one that statically grow on the pseudomorph. So you destabilize the garnet, you do sillimanite biotite, and then you recrystallize another garnet generation. And this is exactly here what happened. So there were a garnet before, is transformed into pseudomorphose, and after inside the pseudomorph, you have a new nucleation of garnet. And you can see it's really beautiful. You have this new tiny garnet that nucleated, and you can see in the middle there is the sillimanite and biotite mineral. And you have also some inclusion of sillimanite that are trapped inside the garnet, which is never present in the oldest garnet, obviously. So only in the new garnet you have the sillimanite inside. And so it's post-kinematic. It's clearly post-kinematic. And you can see, for example, here, you have the main foliation made by biotite and sillimanite. And you can see that the ilmenite blades that are stuck inside the main foliation, when they enter in the edge of the garnet, they are still aligned with the main foliation. So you can see that it's a static overgrow of the garnet on the pseudomorph. It's really obvious. And such garnet, they are also present in the mafic rock. This is an amphibolite layer also inside the basement. And you can see that you have a very beautiful hydral garnet that grow inside the pseudomorph of non-deformed amphibole and plagioclase. This domain is not deformed. You can see from the color, and all this domain is deformed by the amphibole. So even inside the mafic rock, you can find this signature. So we have a static event that brings the sillimanite. And you can see here also there is sillimanite growing inside the main foliation. The sillimanite is mimic the oldest foliation and the main foliation because it's growing inside the cleavage plane of the biotite. And you can see in some domain, where is my mouse? Here. In some domain, when you enter in the quartz, you can see this beautiful radial aspect of the fibrolytic sillimanite, which also testify that we are in a static domain of growing. So we have a post-main foliation static event recorded in this part. And I told you pseudomorphs are really important, the pseudomorph of garnet. But we have also pseudomorph after sterolite. So this is the pseudomorph, the sterolite of the previous unit. And this is the sterolite from the sillimanite area. And you can see the shape of the sterolite is preserved because everything is static. And you can see inside the pseudomorph that we have sillimanite, which is prismatic this time, and biotite. And this is really beautiful. And when you have basal section of sterolite, you will find also rounded pseudomorph, and they are much more conservated. And respect to the garnet pseudomorph, you can see that the one of the sterolite, they are much more rich in sillimanite and much more poor in biotite for a simple reason. Like if you look the chemical composition of sterolite respect to garnet, there is much more aluminium inside the sterolite. And so this is the reason why in the pseudomorph of the sterolite, you will have much more sillimanite that will be able to grow. And the one of the garnet will have much more biotite. And now, if we move to the transition between the sterolite unit and the sillimanite unit to understand which are the processes that will go from sterolite to sillimanite, you will find this very beautiful polymetamorphic garnet. It's one of the most crazy garnet I have seen so far. And so you have three growing phase of garnet that are separated by two phases of dissolution of garnet. And if you look, for example, the calcium content and the manganese content, you will see that in the calcium especially, you will have a preserved core of garnet and rim. This is the rim of the garnet because if you look inside the manganese, you can see that you have low manganese and the highest manganese. So this is the core and the rim of the first garnet. You can see that this first garnet has been dissolved. And after another garnet have grown here. So this is the mantle of the garnet, which is extremely full of inclusion. You can see here on the mantle of my garnet, it's really dark because it's completely crowded of micro inclusion. And if you look careful, for example, with some ilmenite and the others, you can see that they are all oriented. So we know that there is the foliation phases, the deformation phases that occur before that this garnet grow. And so this is what I have drawn here. You have a dissolution of the garnet core. You have deformation phases that make porphyroblasts of the core of the garnet. And after there is a static regrow of the garnet that will trap the old foliation inside. And this is really beautiful. And if you look inside the micro inclusion that we have of the mantle, what can you observe? They are polymineralogical. They are crowdy of mineral. They are staurolite. Sometimes inside the staurolite, you can find the inclusion of kyanites. There is plagioclase, there is quartz, there is biotite, there is muscovite, there is monazite, there is kyanite here again. So they are really, really beautiful and really nice microstructure. And after that, you can see that this mantle of the garnet has been dissolved. You can see, and it has been regrow a new rim external of the garnet free of inclusion. And if you are looking in this rim, what you will find? You will find the sillimanite included inside the garnet. And this is exactly the static event that we have observed here before in this crust. And so if I resume, you have the holder core, the deformation, and then the growth of the mantle that preserve the staurolite inside, the staurolite of this domain here. After you deform again our porphyroblast and you dissolve it another time, and after you are able to grow the final rim statically after the main deformation where you have the sillimanite inside. And so, yes, and after now, if I go back to the bottom part of the session where you are more in the green species condition, what you will observe? You will observe that the staurolite are destabilized in plagioclase. You can see it's corroded, and you can see there is still the shape of the staurolite here that are voided by the biotite. And if you look here, another staurolite, you can see that the staurolite here, when you are going more toward the green species condition, is destabilized. Here there is a little overprint of sillimanite at the edge, so we have very beautiful microstructural petrology. And if you go toward the green schist, you are completely retrogressing the session here. So you can see there is a new crenulation that is developing inside the main foliation. This is the main foliation, and you can see it's overprinting by a new crenulation. And you can see that the garnet porphyroblast, they are completely not in equilibrium and replaced by chloride plagioclase. But you can see sometime in the pressure shadow, oops, sorry, in the pressure shadow of the garnet, there is still biotite present. And if you look inside the ilmenite blade in the main foliation, you can find also some biotite preserved. So we know that this part was retrogression of this domain in the middle of the staurolite. And in fact, we think this retrogression and this regulation is due to the activity of the Lugano-Val Grande Fault, because we are exhuming this upper part of the middle crust toward shallow environment, and we are retrogressing him by by fluid percolation. So it's really classical. And on the field, which is exactly what we observe, this is pseudomorph after garnet, and now it's only chlorite. You have chloride ball of old garnet. And if you look also staurolite, this is ex-staurolite, and now it's only chlorite stuff. But you can still see the shape of the chloride staurolite inside the metapelite. So, and so this is the reason why that it's really important to look for pseudomorph when you are looking this kind of basements, because you will be able after to reconstruct the tectono-metamorphic evolution. So this is the integration of all the things that we have observed in the beginning. So in the beginning, we have the staurolite unit, which is with the kyanite stability field, which is between two deformation events, the main foliation event and the oldest foliation event. And after the main foliation event, you have a static overprint, thermal overprint that brings the sillimanite. And after you have the cooling of the Lugano-Val Grande Fault into green species condition. So as you can see, we have a very, very complex tectono-metamorphic events of the basement. And now that we have which is the PTt now about that now we have the tectono-thermal evolution. So which are the most promising rocks to study this? So we will focus about the storolite unit and the sillimanite unit, because at the end, if you think about the section, you can see that it's not anymore a Barrovian sequence, because I have proved you and show you that all the units, all the section before was in storolite facies condition, and the southern portion was overprint in green schist facies condition, and the northern portion was overprint in the granulitic facies condition. So it's just overprint and not anymore Barrovian sequence. It's just apparent. And so for this reason, we will modelize the oldest lithology, which is the one with storolite, and we will see how the storolite can be coming to sillimanite. And so we build pseudo-section according to the bulk composition in the MN system of the storolite unit. And this is the pseudo-section that we obtain there. And how we constrain our pseudo-section. So to start, we took the garnet core and the garnet rim of the core, and we were able to modelize the garnet isoplate of this composition with the maximum and minimum value, and we have constrained where the garnet core rim, inner core, outer core, sorry, is growing according to the isoplate of the garnet. So it falls here, close to the stability, outside of the stability field of the storolite, very close. And you can see that in this pseudo section, there is something really interesting to note, is in this domain here, we are outside of the stability field of the garnet. And you will see after that it's really important. And in this domain, we will be inside the stability field of the storolite. And in this domain, we will be in the stability field of the rutile, and all this is ilmenite. And here there is the aluminosilicate triple line with the sillimanite, the andalusite, and the kyanite domain. And in fact, we constrain our peak assemblages of the peak assemblages of the rock by the garnet mantle. This is where you have the highest pressure mineralogical assemblages with the storolite and the kyanite assemblages, which fall inside this domain. We found some relics of rutile also that attest that we are inside this domain. And after, we have to check about the modal amount of garnet inside the rock, the modal amount of storolite, the modal amount of biotite, and the modal amount of sillimanite to try to understand what's going on in your rock. And as you can see, starting from the garnet core toward the garnet rim here, which are full of polymineralogic inclusion, we are entering inside the storolite stability field here. And what happened when the garnet enter in the storolite stability field? We have a little breakdown of the garnet. Like you have the modal amount of the garnet, which is decreasing from 6 to 4.5%. And this consumption of garnet is promoted by the storolite growth with the formula of the garnet plus storolite that gives garnet plus chloride, sorry, that gives storolite plus biotite. And this is the reason why when we were studying the garnet, we have a dissolution phases between, I will show you here. This is the reason why we have a dissolution phases of the garnet between the mantle of the garnet and the inner and the core of the garnet, because we are crossing this domain here that reduces the modal amount of garnet and to make the growth storolite. And this is the same that we are observing after for the exhumation process. We are exhumating our rock after the baric peak toward the sillimanite domain. and we are consuming garnet, and we are still remaining in the storolite, the storolite field activity, and we are consuming garnet. And in fact, in the deepest part of the crust, there are many pegmatitic dikes, and other authors have set the PT of the pegmatite by looking fluid inclusion, and they are set into this domain. And in fact, our PT model pass also inside this domain here, the small triangle. And this is how we are constraining our exhumation. But as you can see, we don't enter immediately inside the stability field of the sillimanite. We firstly exhume toward this very low domain because in some portion of the basement, there are some description of Andaluzite bearing mineral inside the metapelite. Unfortunately, we were not able to observe them, but they are present and they are before the sillimanite. So we must pass to this domain and pass by the sillimanite and consume the garnet. So this is the reason why the garnet mantle is consumed before the new growth of the sillimanite and the new growth of the garnet. So here you are out of the stability of the garnet. And in fact, now when you enter in the new stability field of sillimanite, you will regrow the garnet. And this is the third generation of garnet, which have the sillimanite included. So in all where you are doing the pseudomorph of garnet and then the overgrowth of garnet on top of this. So as you can see, the pseudo section is fitting with what we have observed in the macroscopic things also. And we make some average PT results because we have to use another constraint to constrain the high temperature PT assemblages because our bulk composition that we made from this pseudo section is made of the storolite assemblages. And so after there is pseudomorph and after there is new garnet, which will react. And we cannot model this with the previous pseudo section. And so this is the reason why we make the average PT calculation with the equilibrium assemblages of quartz, biotite, garnet, muscovite, plagioclase, sillimanite, and ilmenite from the granulitic rocks. And we obtain this peak temperature stage condition of almost 700 degree and 6.3 kilobar of pressure, but unfortunately with a lot of error. As you can see, the error is big on the pressure. And so now that we have a PT condition, so the PT condition that I have here, so we have to try to date the PT condition. And so which are the most promising unit to date it? So we have date the mica schist, we have date the pegmatite, and we have date the sillimanite, the storolite bearing mica schist also. So we have date inside the storolite, we have date the monazite. Inside the sillimanite, we have date the monazite and the garnet. And inside the pegmatite, we are lucky because there is some magmatic garnet inside because they are really differentiated. And so we were able to also date the garnet there. And this is what we obtained from the dating. So if you look the monazite from the storolite unit, they are really poichoitic, and you will always find a consistent age of roughly 320 million years, which is Carboniferous, which is completely in agreement with the Variscan orogeny that I have discussed in the introduction, the Carboniferous orogeny. So this is the trace of the Variscan orogeny, so no problem. But if you look inside the granulite facies condition with the sillimanite, what you can observe? You can observe that you have monazite with a little rim, and you can see that the rim is free of inclusion, and the monazite is full of inclusion again, like the one that we have observed before. And you can observe that the main crystal has the same age of the one of the storolite unit, like 320, 315. So still record Variscan ages. but you can see that there is an overglow of a very tiny rim on the edge of the monazite, which gives Triassic age. And this is what we obtain. So, here we have a crystallization age of our metamorphic event that is involving. And this Triassic age is what the metamorphic overprint of the crust from the rifting. And now, if I move to pegmatite and date the garnet, how we date the garnet from pegmatite? We did lutetium hafnium age from garnet, so and mica schist. So this to proceed this we did by total dissolution of garnet. So why we choose this method is because the new garnet that grow inside the mica schist is completely free of inclusion. So you don't have problem by dissolution saying, I have mixed analysis and this not happen. And this is exactly the same from the magmatic garnet from the pegmatite. They are extremely homogeneous, only one phase, free of inclusion. When you pick them, they are completely transparent, and you are sure that you are not doing mixing analysis by dissolving them. And as you can see, we dissolve alico of garnet and the wall rock composition, and we have a very beautiful line with a Thermo-Triassic age. This is the transition between Permian and Triassic age, and a Triassic age of 235 million years. So this is perfect. This is exactly what we want to see. So that this guy is overprint by late Permian to early Triassic thermal events. And this static, this is what we have observed. And in fact, if you look this pegmatite and the hosting mica schist, you will say, but look, it's weird. I have the pegmatite intrude the mica schist, but the garnet of the pegmatite is older than the mica schist. It's weird. Normally, it's the opposite. Normally, the one that intrude the other one should be younger, but is older. And this is the reason of the pseudomorph that I told you before in the presentation. Like the old garnet here was completely destroy and regrow after that this pegmatite intrude and recrystallize. So this is exactly the reason why that the age of the garnet from the hosting rock is younger than the age of the garnet from the pegmatite. So everything makes sense, and it's also in agreement with the texture that we are observing in the rock. So perfect. And so here it's a tectonic sketch of the monazite and the garnet respect to the rock that we have observed. So the garnet are inside the pegmatite. Some pegmatite are deformed, some less, but we know that there are one swarm generation of pegmatite according to the composition. And also in the literature, people who explain that these pegmatites are seen to post deformation of the main foliation. So by dating the garnet from the pegmatite, you can approximatively be able to date the age of the main foliation. And we know by this way that the main foliation occur close to the transition between the Thermo-Triassic domain, so at 250 million years. And you can see that the monazite and the garnet, the new garnet grow inside the pseudomorph. They are affected by this late static event of 235 million years. So it's perfect. And there is also some monazite that also record in the main foliation that are wrapped around the edge of the same edge from the garnet from the pegmatite. So you see, we have two kind of data set, one of lutetium hafnium of garnet, one of uranium lead of monazite, and they are all fitting each other. So if you use only one, it could be very, very weak, and you have to use both of them to show that you have good data about this domain. And in fact, after that we have all this, we can reconstruct the completely PTt path of the Dervio Olgiasca. Like we have the initial garnet that is reworked by a main foliation. And so the main foliation has to be older. And after you go to the baric peak, which is Variscan, with the chiral stability field very close to the liquidus. And after you have a huge exhumation process. And it's correct, you see, you have a huge deformation during the exhumation process because it's where in the rifting process you are making the extension. You are extending the middle crust of the Adriatic margin, to during the Late-Permian to be able to exhume all the rocks toward this shallow condition. And after you have the static thermal event late that overprint all the rocks that go inside the sediment-facies condition, very close to the melting again. So you don't have this kind of classical decompression path that you observe at the end of the erogen that go directly from the kyanite stability field to the silimanite stability field. It's not happening in this case. And after here, there is late faulting, like the Lugano-Val Grande Fault that start and make the final exhumation. So you see, we have a very beautiful PTt path at the end. And so our data is coherent because this is only the Dervio Olgiasca unit, the metapelite that we are studying from the pseudo section. And you can see this is all the data set, geochronological and thermochronological that we have from the unit. And you see they are spreading from 300 million years to 120 million years. And so you see, it's messy. But in reality, no, it's not messy at all because the dot with the red border is the data that we collect. And you can see that we suspect that there were a Variscan inheritance in the basement, and we show it by doing uranium lead on monazite. We found the Variscan event, no problem. But we also found the Permo-Triassic event with the main deformation here of the extension of the middle crustal level. And we found also the static thermal event that affect the continental crust later on, just following this extensional event. And no one was able to find it before because all the edge here that you can see with the stars are on muscovite, biotite, and they are mostly rubidium, strontium, argon, potassium, argon, and they are cooling edges. And people at the end, in the beginning, expected dates here the edge of the main foliation by dating the mica and the biotite inside the main foliation. But it's not working because when you date these guys, you are dating a cooling edges because between the main foliation and after the main foliation, I mean, there is a thermal event that go towards silimanite towards 700 degrees. So you are completely resetting the edge of the mica. And so this is the reason why when you are dating in this unit the mica, you are not anymore dating the tectonic event of the unit. You are only dating the cooling edge of the thermal anomaly that is at the early Triassic. And after you can see if you are looking the fission track of apatite and from zircon, you can see that you have the progressive cooling of the margin till the Jurassic and Cretaceous. So cooling history. So this is why, to me, when you are doing things about multiple metamorphic stages, it's really important to have the very good control about the tectono-thermal evolution of the unit and try to date crystallization age rather than cooling edges because you can misleading your information like this, all this mica biotite. And so I go fast because I lose a bit of time. And so this is what happened at the end on microsection. So the core of the unit is the oldest with the Variscan metamorphism, with the storolite. All this story is Variscan. And the deepest part is overprint by a middle Triassic thermal overprint of 232. And the shallow part in the south is overprint by the Jurassic faulting, the detachment that equilibrates things in Grish's facies. So as you can see, beautiful Barrovian sequence, but not at all. It's completely polymetamorphic. And so now I quickly, it's very short, I go with the sedimentary cover over the basement. And this is really important for me to speak to you about this because if you are perturbating the basement with thermal anomaly, you should find it on the sediment. And I will show you that on the sediment on top of the basement, there is a signal of this Triassic thermal perturbation. And so this is the signal. So what happened in the sedimentary cover of the basement? You can see that there is numerous tooth layers, which are in green color, which are inside the Carnian, Ladinian, and on top of the Anisian carbonatic platform. And so this is Middle Triassic, Early Triassic, and you can see that it's linked to the thermal anomaly that we previously date in the basement. And you can see that these Ladinian Cardian volcanoes that do this two layer inside the carbonate, they are very well dated because we know it by the sedimentary stratification. And the people in the literature know that it's between 242 and 237. It's exactly like my thermal anomaly where I have few partial melting also in the deepest. So there is volcanism, it's coherent. And after, if I look at this age also, I have unconformity of the base of the carbonatic platform. There is a small immersion with a karstification here. It's the yellow layer. And so there is a bombing of the continental crust due to this thermal anomaly. There is a little bombing that do this small immersion period of the limestone. So it's also coherent with what we were showing in the basement. And after, if you look inside the carbonate, what you can find, there is a massive ore deposition of galena, which is rich in lead with sphalerite, of zinc and fluorite with fluor. And the people, according to the stratification, they were able to find that all this hydrothermal, because it's all hydrothermal process that occur inside the sedimentary cover. They are between 247 and 225 million years. And so this is exactly the timing of the cooling of my thermal anomaly led by the white mica. So you can see that we have a perfect signal also according to the sediment, the stratification on top of the basement. And now here I summarize all the information. You can see my thermal anomaly with this, it's completely fitting with the three kind of edge that I showed you before. And the activity of the Lugano-Val Grande Fault, the big extensional coastal scale detachment that I explained you previously, you can see also this is cooling of the thermal anomaly. And this is what we observe. And so this is the final sketch. It's a proposal of sketch that what happened here in the Central Alps, in the Southern Alps. Like in the beginning, you will have this kind of Bariscan orogenes. It's like a very thick crust. It was a thick crust because it's an orogeny, and this crust was shortening by thermal relaxation of the crust. And in the Permian time, you have this kind of small graben that occur with volcanoclastic sediments. And the thinning of this crust due to rifting bring the mantle close to the surface, and it's making adiabatical decompression, and the mantle is melting. And so you have a lot of gabbro during the Permian, gabbro underplating below the lower crust. You have magma differentiation, contamination with the crust, and more you go toward upper crustal level, more you will have differentiated magma with so gabbroic in the bottom. In the top, you have more diuretic, and when you are more to the top in the upper crust, you will have granite and volcanism with volcanoclastic deposit that fill the sedimentary basin of Permian graben. So all clear. But when you move to the late Permian, it's what we have observed in the Dervio-Olgiasca Zone. It's our study here. Like you can see that the deformation start to localize in the middle crustal level, and you can start to extend, to extrude your middle crust, and you thin it. And by thinning this lower crust, you will keep rising the mantle, and you will keep rising the lower crust toward the upper crust, because as I show you in the introduction, during the rifting process, this middle crust will tend to be removed, because if you make a rheological profile, it's the weakest point of the crust. And so all these things are extruded and minonitized and deformed. And so what will happen after, in the middle Triassic time, you have extruded a bit of middle crust, you have thinned the middle crust level, and you have bring the lower crust more close to the surface. And what happened? The lower crust is much more warm, and so you have thermal conductivity that will warm your middle crust. And this is the static event that we observe. We have overprint with silimanite and whatever by thermal conduction from the under lower crust. And after that, so this is our thermal anomaly. And after that, in the late stage, you cool the thermal anomaly, and the final cooling localize the deformation, and you will have this kind of listric detachment that are crustal scale, and you are in the main part of your rifting where you have a huge accommodation, lots of filling of the sedimentary basin. You are doing the carbonatic platform. So this is all the dolomite in Italy. They form during this period where you have a lot of accommodation and subsidence of the basin. And if you look according to the data of the basement, you can see that all these late large-scale faulting that are from late Triassic to early Jurassic, they are all when the basement is cooling. It's all cooling that produce this kind of stuff. And so now, if I go back to the large scale and I start go back from the introduction, you can see why we love to study the basement and the architecture of rifting in the Alps. It's because it's a beautiful lab to understand what's going on now in present day below, because we have no access of what's going on below. Or even if you are doing drilling, by doing drilling, you don't see well the structure, the fault, the thermal anomaly, on this kind of things. So I suspect that here you can have similar things that what we observe in the Monte Generoso Basin. And so you see at the end, I mean, me when I see the mountain in the Alps, it's not mountain, it's passive margin. So I don't see here mountain, I just see passive margin. And this is why this is a beautiful lab for us to study. And so this is all the wonderful people that work with me that I have present in the introduction. And if you want more details, I was a bit too confused during this presentation. You can find this in these two papers that are much more well structured and much more maybe well present. And that's it.
Thank you so much, Christophe, for this very nice presentation and also with this very nice introduction you provided us so we could understand it. It's quite nice that you ended with this. I don't see mountains, I see passive margin. That's very cool.
Exactly, absolutely.
Yes. So we invite everybody from the chat to send their comments and questions, and we will start with our own questions. Regiane?
Yes, thank you, Christophe, for the presentation. It was really nice. I really enjoyed to study all this thermal evolution and also see these landscapes of the Alps. That's really
yeah.
I was there 12 years ago, and now I can remember.
You should go back.
Yes. And I have some questions. There is some there is difference in the biotite composition in the starolite pseudomorphs, in the garnite pseudomorphs, and in the biotite in the matrix of the rock?
Yes, there is the ratio between the iron and of the biotite is changing, and in fact you can see that when you are inside the silimanite one, it's more and you can see the difference of the increase of temperature. So if you by microprobe, it's in the article we make in the thin section structural position of the biotype, and we very well observe that there is a two or more kind of family, because as you can see there is a lot of phase. You can have till 4 generations of biotype, and so because some are preserved, some maybe can be re-equilibrated, but yes, we observe this absolutely.
And did you try to integrate the biotite with the silimonite in the pseudomorphs to see if it has similar composition to the garnet or not? In the pseudomorphs?
To mean by pseudosection?
No, I think I was thinking about if you can think about it in this thermal evolution, if you have chemical exchange during this in these pseudomorphs trying to integrate the composition of in the pseudomorph of the biotite plus the silimanite, and just to see if you have the same composition of the garnet or some previous composition, or I don't know if there is some chemical exchange.
You don't have exactly the same composition because the manganese will not go inside the silimanite and will don't go inside the biotite. So and then the calcium also from the garnet. And so usually you will find some tiny annex mineral, which could be apatite or could be xenotime or maybe tiny monazite that will absorb the manganese or for apatite the calcium, for example. But they are really tiny because I don't know if you remember I don't know if you see the presentation, probably yes. But if I come back to the composition of the garnet, so you can see here from the composition that it's really a almandine-rich composition, and we have not so much manganese and very. I mean, here you can see a lot of calcium, but the calcium is very short, small domain, so we have very poor calcium, poor manganese, and high rich in iron and magnesium. So this is the reason why the annex mineral, they are really small. They are really marginal. Sometimes you can have a bit of also ilmenite. They can accommodate the excess of iron and this kind of thing. Or titanium. Or titanium by opposite reaction, when you recrystallize the garnet, the titanium don't enter well inside the garnet composition, so you are trying to form some ilmenite blade in the surrounding of the garnet also.
Okay, nice, thank you.
Christophe, I don't know if I missed something when you were saying, but I remember in your sketch for the metamorphic evolution, and it's so cool. I think we as Brazilian, we are very jealous that you have all this preservation of inclusions and cores.
Yes.
It's not so common here. So it's really cool that you can use that to reconstruct your metamorphic evolution. And you mentioned that you found the kyanite. Is that the same rock you had the pseudo section? And how is that the evolution? Because there in the chart, that would be like the pressure peak, right? Can you
Yes,
tell us?
the kyanite is in the pressure peak. Where I found where is.
Can you maybe just put as a presentation? It's like in the PowerPoint mode, and then
This one.
Yes. Yes, perfect. Thank you.
Yeah, you see the kyanite is inside the baric peak. Only here, because it's inside the mantle of the ground. It's because it's the only place where we were able to find kyanite, and the kyanite is never is really rare because, for example, we never observe any pseudomorph after kyanite in the rock, and we only found as relics inside the garnet, but not exactly inside the garnet. It's inside the pseudomorph of the garnet. So,
okay. And is that the same sample you modeled for the thermodynamic modeling?
no, not exactly, because
it's
in
the
fact,
other one.
Yeah, for the thermodynamic modeling, we model the core of the sterilite unit to be able to have the most representative things, because it's the most oldest rock that will be transformed by the cinemanic one. So this is the original bulk composition, because in fact we have tested according to profile, and it's very homogeneous metapelite with similar composition. So we were able to say, if we make a model here, we will be able to modelize how will be the silimanite appearance inside my rocks. Because if I start to model the silimanite rocks by itself, I will not be able to understand the sterilite one, because the bulk composition will be already modified. So this is why at start we start to constrain this one. And in fact, the fully metamorphic garnet, you can observe here only at the transition. If you go too far, it's overprint. And if you go too low, you don't have the silimanite overprint. So you don't have this you don't have this overprint on the garnet. So it's really a very narrow place on the field. It's maybe 20, 30, 50 meters. And so you need really to have the good position for your sampling position. It's really important.
Yes, that's a very important message. And did you find any evidence of melting? I know it crossed your path crossed
Yes.
shortly, but I mean, did you find anything that could?
Because in the no, it's here. So here when we are in the sedimentous condition, when you are looking inside the rocks, they are like we are very close to the liquidus domain, the line of melting, and we have few portion, but really like mini centimeter scale where you start to melt and you start to destabilize the white mica and keep the biotite. But they are really tiny and really marginal. So this is why we are also confident that we are extremely close to the solidus or almost inside. We are at the beginning of the partial melting, but not yet. We are really borderline.
Okay, thank you, Christophe.
You're welcome. I don't know.
So,
It's green, no, it's here. Tac, voilà.
Yeah.
we have some comments here, Christophe, someone.
Yes.
There's info here too.
Yes, they are
Thank you
all
for the
saying
comment.
how
Thank you
nice.
from,
Yeah.
thank you.
And Christophe, I have one last question regarding the age for the monazite. It's so cool that you had this older age of 315.
Yeah,
It's
312,
very, yeah, it's
16,
very impressive. And are these grains like in the matrix? And how can you correlate these? Do you see like because you had some spreading the Concordia age, and you took like the oldest and the younger, but do you see this as continuous growth, or do you think there was some disturbing? How do you interpret?
No, it's not a continuous growth because I mean, if we look inside the fin section, we see that the how can I say? We see that the monazite they are in the fin section. We according to the position of the monazite, we know that they are between the two falling deformation events. So they are and between the two deformation events, there is because there is the main foliation which is vertical and it's axial plane folded all the generation of foliation. And if you look into the preserved old deformation, you don't find monazite. And the monazite that you will find is wrapped by the main foliation. No, it is not wrapped. It's wrapped by the main foliation, so it's before. And so it's between the two deformation events. So when you have the barric peak where there is the kyanite and this kind of thing. And in fact, if you look inside the garnet, it's full of polymineralogic inclusion, as I show you. But as I show also on my figure inside the monazite, it's the same. It's full of polymineralogic inclusion. They are extremely tiny. They were very difficult to investigate. And we know that we have the same habitat as the garnet. And so we are expecting that it should be there. It makes a lot of sense. And after, there is no growth of monazite for sure because there is this sharp border between the rim of the monazite, which is free of inclusion, this one. And it's much more difficult to measure because even if the monazite, I can show you on the screen, it will be more better for everyone to understand where I am on a picture. Yeah, you can see they are very full of inclusion. And we were really lucky because if you look the size of the monazite, you see, sometimes it's like 200, 300, 400 micron of length. So we have really big crystal. You can saw them also from the fin section. They are really clear. And the problem is always the same. It's about rim growing. Like you need to have enough manganese or to be able to grow the rim of monazite. And you see the rim is really small. And so we had a lot of problem in the beginning to measure the rim because you need a spot that is in a good position to don't have, this kind of mixing analysis that are here or here. that will be, for example, this edge of 220. They are mixed edge between the core and the rim, because at the end, when you are doing we do by sync in Lausanne, in Switzerland, and you can touch a little bit the core of the monazite below. So that's why, unfortunately, you see, we don't have so many edges that we have taken into consideration, because we really need to have a clear spot and try to find. I have other picture, but even if you see a rim, you need to be able to have the technique to be able to measure it. And so sometimes it could be challenging according to what we have in the field section. Indeed.
Thank you, Christophe.
But this is the reason why there is the lutetium on garnet, because people can say, you don't have so many samples, you have probability of mixing edges, so it could be weak. And so this is the reason why we did also the lutetium hafnium into garnet to say, look, I have the same edge from the monazite and the same edge also from the monazite rim, and the same edge from the garnet. So that's why when you are doing two crystalline edges of geochronology, it's much more better to make a strongest argument and strongest data.
Yes, that's also a nice message you left for us with the cooling edge versus crystallization edge.
And the cooling edge is really impressive in this region, because you want to date mica and biotite, but you don't understand what you're dating if you don't pay attention, and you have to be really careful about mica. So that's why now I'm careful about mica. That's why I prefer crystallization age if it's possible. It's always about what we have, So.
I just have one really quick question, a last one, about the first landscape, this photo. The lake is glacial, carved by
Yes.
glass. Okay, just that.
Absolutely. No, but you're right. It's really nice geomorphology.
Yeah.
Like you have two glacial valley that goes here, and the lake is I think it's 400 meters deep. Like there is a 400 meters down in the lake, so it's still eroded inside by it's glacial lake exactly. And for example, you see this valley here. This valley is east-west, and this valley is doing Insubric Line. And you see the glacier dig inside the Insubric Line, the
Nice.
main discontinuity of the Alps. It's here, you see, north. This is the Como Lake, north Insubric Line, and the glacier erode exactly here. This is really beautiful. And in fact, if you look the satellite view of the Alps, you can see that there are many faults in the Alps. For example, the Insubric Line is here. You can see the glacial valley is going here. After it's dismembered by a fault here with the glacial valley inside, and after you have the continuity of the Insubric Line that goes here toward Austria, Vienna, and whatever. So even geomorphology could tell us the structure.
Nice, thank you. Alice?
Thank you, Christophe, for the great talk. Thank you very much. And we invite everyone that is watching to look for our previous presentations on our YouTube channel. So thank you very much. Bye-bye.
Thank you.
Thank you, everyone, for attending. Thank you, Christophe.
Thank you, Christophe. Thank everybody here. And follow us in our social media.
Yeah, follow Petrography.
Yeah. Bye-bye.
Ciao, ciao.